All right, so we can define, we're going to talk about just a few more little topics. So bond energy. We defined the bond energy of a bond, so a bond between A and B. Your book happens to denote it with the letter D. I don't know, some other books use BE, so I may end up mixing them up. I think I use D in everything. So bond energy denoted with a D. It's the average enthalpy change for the breaking of a bond of a molecule in its gas phase. So how much energy is required to break a bond? And it's a little bit of a misnomer, or misunderstanding sometimes. You always have to put energy in to break a bond. So no matter what kind of bond it is, you have to put energy in to break it. So enthalpy is delta H. So yeah, what I was saying. So it always requires, to break a bond, always requires energy. So energy is, delta H is positive. You have to put, or the bond enthalpy, the bond energy, let's do it that way. The bond energy is positive. So bond, D. D is positive. So the bond energy is positive. When you form a bond, however, it's the same value, but it's negative. So energy is released when you form a bond, energy is put in when you break a bond. And so what we'll find out is that the overall delta H for any reaction is approximately equal to the bond energies of the reactant. So how much energy do you have to put in to break the bonds, minus the sum of the bond energies of the product. So again, in other words, how much energy is given off. So we sum all the reactants to find out how much energy you have to put in, and then we sum all the bond energies of the products. That's what comes out, and then overall we'll see how much is needed for the reaction. So it's a little bit of a I think when you're younger and you learn some biology and it says, well, energy is stored in those bonds. Well, it's kind of true, but keep in mind that you still always have to put in a little bit of energy to get the thing going. So you have to, I think that's where the activation energy comes in. You have to put some energy in to get the reaction going, and then you get energy out. So it turns out that if it takes just a little bit of energy to break the bonds, and then you get a lot of energy out when you reform the bonds, then ultimately you're getting more out than you put in. And so that does release energy, and that's an exothermic reaction. But if it turns out that you have to put a lot of energy in to break those bonds, and then when you reform new bonds, you just get a little bit out, overall you're putting more in than you're getting out, and that's an endothermic reaction. So anyway, we're going to sum the reactants, the bond energies for the reactants minus the bond energies of the products, and we'll get the overall delta H. So we did this back in chapter 5, I think, and now we're going to just do it from a different perspective. So the next slide, and actually there's a bigger table in your book that lists some bond energies. Okay, so here's the table, and actually the table in your book is a little bit longer, has some more, so if you can't find the one you're looking for on this table, look in your book. But you can see here, like a HH bond is 463. These are all in kilojoules per mole, so 436 kilojoules per mole. A CH bond is 415, a CNHN bond is 360. God, I can't talk, 390. An OH bond is 464. Anyway, do notice that we said that, you know, a single bond is different from a double bond. So a CC single bond is 345, a CC double bond 611, and a CC triple bond is 837. There's also a C, sort of hard to make that triple bond, but you can, at least you can tell that that's what it is. And so make sure and look up the correct bond. Yeah. Okay. So like I was saying, if you have the bonds broken from the reactants minus the bonds formed in the products, this is probably the easiest way to look at it. So the delta H for the overreaction is the sum. So sigma means sum. We take all the bonds broken, the bond energies for all the bonds broken, and then we subtract the sum of all the bonds formed in the products. And so you can actually look and see which bonds are being broken. You can look up the values and do this calculation. All right, so let's look at this example. CH4, let's find the delta H for this reaction. So we have CH4. I'm going to go ahead and draw it out for you. These are all pretty straightforward molecules, so you can see the bonds. Oops, Cl, Cl. So there's a CH4, and do be careful that if there's any coefficients that you multiply by the coefficient. This one's pretty straightforward because they're all 1 to 1. Anyway, there's a Cl-Cl bond. Here's the CH3Cl, so HHHCl, and then an HCl bond. So if we look by inspection, we see that to get from the reactants to the products, we're going to have to break one CH bond. We're going to have to break a Cl-Cl bond. Then we're going to form a CCl bond, and we're going to form an HCl bond. So one CH bond is broken, one Cl-Cl bond is broken, and then a CCl bond and an HCl. So we can look up those values. And let me give you a little hint. Sometimes if you have a hard time seeing what's happening, I think this one's pretty straightforward. But if you really have a hard time seeing what's happening, one thing you can always do is you can break every single bond and reform every single bond. And then the ones that didn't actually break cancel each other out, because to break them is a certain amount, to reform them you get the same amount out. So you'll actually, it may be a little bit more work, but if you're confused, just break every single bond and form every single bond. So we could break 4 CH bonds and then form 3 CH bonds in a Cl, but I think this one's pretty clear what we're breaking and what we're forming. So now we just look up those numbers. Okay, so then we just look up the numbers and we see delta H is the bond angle of the CH bond, bond energy of the CH bond plus the bond energy of the Cl-Cl bond. Sum those up, then we have the bond energy of the CCl bond plus the bond energy of the HCl bond, and sum those up. So we have 415 plus 243, and then minus the sum of 330 plus 432. Look those up on the table. 658 minus 762 gives you a delta H of negative 104 kilojoules. So overall, we put less energy in than we got out. So this is an exothermic reaction. So here's another example. Let's find the delta H for this reaction by using the bond energies found on the table. So let's kind of look at it. And be careful, because like we know, like we saw, a double bond is not exactly twice a single bond. They're different, but so in this case, notice what we're going to have to break that CC double bond and form a CC single bond. So we're breaking a CC double bond. Now all the H's, these two H's stay on, these two H's stay on. Here's a HH bond that we have to break. And then we're forming 2 new CH bonds. So we are breaking a CC double bond, we're breaking an HH bond, and we are forming a CC single bond and 2 CH single bonds. So we can look those values up. Again, the sum of all the bonds broken minus the sum of all the bonds formed, the CC plus the HH, minus 2 CHs plus a CC. And be really careful, make sure you do your parentheses, and because you want to subtract the whole sum of all those. Okay, so 611 plus 436 minus 2 times 415 plus 345 gives us negative 128 kilojoules per mole. Okay, so finally, let's circle back around and look at ionic bonds. So we kind of started with that. We talked about how ionic bond is one kind of bond. And now we're just going to talk real briefly, finally, about ionic bonds. So again, we know an ionic bond is just a chemical bond formed by the attraction between positive ions and negative ions. And of course, if we're going from elements to ions, this involves a transfer of electrons from one atom to another. So metals usually give off electrons, and nonmetals will gain electrons. Now, we already know how many electrons in general that atoms gain or lose. And why do they lose that number? They're losing the number so that they can be isoelectronic to a noble gas. So sodium usually loses 1 because it has that 1 valence electron. Magnesium loses 2. Chlorine likes to gain 1, and so forth. So we know that noble gas configurations are particularly stable because they have a full valence shell, and so that's why those ions want to do it. So, and we've talked about this before, but now we're going to get just a little more detail. So we know that when atoms lose electrons, they become positive, and positive ions are called cations, and we can always remember which is a cation because the cat with the T is positive, so cations are positive. So here's an example for sodium, and now we've got the electron configuration in there. So sodium has the same electron configuration as neon, and then it has a 3s1 electron. So if it loses that 1 electron, so here they're showing the electron being lost as one of the products, and now sodium ion has the electron configuration of neon. Obviously, it's not neon because it has a different number of protons, but it has the same electron configuration as neon with 10 electrons. So an atom that gains an electron becomes an anion, and we can remember that it's a negative ion, and so that's how we remember that one. And so an example of that would be chlorine. So we know chlorine has the neon core 3s2 3p5, and now if it gains an electron, so now we're adding an electron to it, where does it add? It adds to the last opening in the third shell, and so 3s2 3p6, which of course is also equivalent to argon, so we could write it either way. And so we gain an electron or we lose an electron. So then what happens? So let's consider the transfer of an electron from sodium to chlorine. All right, so there's sodium metal, there's chlorine metal or chlorine gas. Sodium will transfer an electron, and now we have Na plus and Cl negative. Interestingly, we know obviously this is a very stable salt and very common for ions to do this, but interestingly, the actual process of taking 1 electron from sodium and giving it to chlorine actually requires energy. And so it turns out that this step requires energy, but then because now these ions are attracted to each other, that's where we're going to actually give off energy. So when they are attracted to each other and form a bond, we call that an ionic bond. And we can show the Lewis electron dot symbols, or the symbols in this case, to actually show the reaction of the electrons being given. So we represent, right, this is just a repeat of that last of that slide way at the beginning, and don't forget these are the A groups, so not they're 1A, 2A, 3A, 4A. And so our valence electrons are the same as the group number, 5, 6, 7, 8. And so these are our Lewis dot structures, and the group number indicates the number of valence electrons. And so now let's say we want to represent the transfer of electrons from sodium to chlorine. Oh, actually, we're going to look at magnesium to. So magnesium has 2 electrons to give, and each fluorine only has 1 vacancy. And so we know that magnesium has to pair up with 2 fluorines. So this fluorine has an empty space, this fluorine has an empty space. Magnesium has 2 electrons, so if it transfers 1 electron to fluorine, 1 to this fluorine, now we have the fluorine ions, the 2 fluoride ions, and the magnesium ion. So this is how we would represent the transfer of electrons from one to another. Now, of course, if it's simple, something simple like sodium, let me use a different color. Let's say sodium has 1 electron and chlorine has 7 electrons. So this one's easier because we can just give sodium 1 ion. So then we have Na plus Cl negative. Again, so just keep in mind that if we have to have more than one, then you have to show both movements. As I said just a minute ago, actually the energy that is required to take an electron and transfer it from sodium atom to a chlorine atom actually requires 147 kilojoules for it to do that. And so you would think that doesn't seem like since it wants to be more energetically stable, well, why would it happen if it requires energy? Well, the answer is that we can get a whole lot of energy released just by taking the Na plus and the Cl negative and having them come together, get close together. So we first have the transfer of electrons, and then when the sodium and chloride actually come together, we actually release 493 kilojoules of energy. And then actually one more thing happens. If when the ions solidify to salt, another 293 kilojoules of energy is released. And so all of this is definitely more than the 147 needed to take the electron in the first place. And so we know that it kind of balances out, or it more than balances out. This is definitely energetically favored. I think we got a picture on the next slide. Oh, so this is called lattice energy. The lattice energy is the negative of the energy released when gaseous ions form an ionic solid. So the lattice energy, well, it's on the next slide. Let's look at. So here's all the different steps. So if we have 1 mole of gaseous sodium and 1 mole of gaseous chloride, I'm going to Cl. Now, to take the electron and transfer it over, we have to put 147 kilojoules in. So now we have our ions. Well, as soon as those ions pair up, we now release 493 kilojoules. Then, for them to become a solid, we release another 293 kilojoules. And so overall, this lattice energy of them coming together to form a solid is negative 786 kilojoules. So the lattice energy is 786 kilojoules. That's how much you would have to put in to undo the lattice, to separate them back out. So the lattice energy is how much you have to put in to separate the lattice, to break the lattice. And so that much releases. So overall, the net amount released is negative 639. So from the start to the finish, releases a lot of energy, and you just had to put that little bit in to get it started. So overall, this is energetically favorable. Now let's talk about electron configuration. So we saw just a little bit of that a minute ago. We know that when a metal loses its electrons to form cations, they want that noble gas configuration. And so we can see exactly down here with magnesium, we had the 3s2 electrons, and now once we've lost the 2 electrons, we have the neon core. All right, so most of the main group elements are pretty straightforward. So Transition metals, however, will also, obviously they lose electrons because they become positive, but what happens is they actually lose the electrons from the highest energy level first. So, for example, like the 3D element will lose the 4s electrons first. So not necessarily the last electrons that were put in. So it's sort of with the main group elements, of course, the last ones in are the first ones out. But for the transition metals, it doesn't quite work that way. So actually the s electrons are lost first. So they usually lose their s electrons, and when we say n, I'll talk about that in just a second. And then if more are needed, then they lose the d electrons. So for example, if we're talking about anything in the first transition row, like chromium or magnesium, manganese or iron or something, so they have 4s electrons and they have 3d electrons. Well, they're going to lose the 4s electrons before they lose the 3d electrons. Now, if it's the next row down, they'll lose the 5s before they lose the 4d. So that's what that means, n-1. So they'll lose the higher s electrons before they lose the d electrons. And then if they have to lose more, they'll lose the d electrons. So here's an example for zinc. So zinc generally loses 2 electrons from its 4s subshell. So you can see here, here's the noble gas for zinc, argon core, 4s2, 3d10. It's not going to lose, so the last 2 electrons we put in were the 3d electrons, but actually it's going to notice it lost the 4s electrons first. So this is the configuration for the zinc ion. It's pseudo-noble gas. It's kind of like it rather keep the d electrons stable. It'll lose the s electrons first. So remember when we talked about the energy levels, the 4s and the 3d are awfully close to each other, and so it just happens to be more energetically favorable for it to lose the 4s electrons first. So that's it for this chapter. What should you be able to do in this chapter? You should be able to use Lewis symbols to represent ionic bond formation. So that was the last thing we talked about. Be able to write electron configurations of ions, which is what we just talked about. Be able to use electronegativities to decide if a bond is polar or nonpolar. Be able to write Lewis formulas and Lewis structures. Be able to write resonance structures if required. So if you have to make a double bond and the 2 choices are the same, you're going to write a resonance structure where you'll write the double bond to each element that are the same write that many resonance structures. You should be able to relate bond order and bond length, meaning single, double. So bond order, first order is a single bond, second order is a double bond, third order is a triple bond. Bond strength goes up as you increase the number of bonds or increase the bond order, and bond length decreases as you increase the bond order. You should be able to estimate delta H from bond energies, so using those bond energies from that table 7.2 to be able to determine the delta H for the overall reaction. You should also be able to predict molecular geometry, so you should know the domain geometry for the overall number of domains, and then also the molecular geometry when you drill down by looking at bonds versus unshared pairs. You should also be able to determine if a molecule is polar or nonpolar.